Today we are going to talk about Charles' Law. So Charles' Law is another one of the gas laws that we're going to be talking about in this unit. The formula for Charles' Law you can see right here. The two variables that we are dealing with here, we are dealing with V, which is volume and is measured in liters, and we are dealing with T, which is temperature and is measured in Kelvin. Now, remember, I have conversions to note down here. To convert from Celsius to Kelvin, you have to add 273. So that means if you had 0 degrees Celsius, that would be 273 Kelvin. So that's something you want to remember. The other thing you want to remember I don't have on here is that, put it over here, another important conversion to note is that 1,000 milliliters equals 1 liter. So that's another important conversion to note. So if you have milliliters, you have to divide by 1,000 to get to liters. The relationship that's going to exist with Charles' Law, you have volume 1 over temperature 1 equals volume 2 over temperature 2. So it describes the relationship that exists between volume and temperature within a gas. And it is going to be a direct relationship. And what a direct relationship means, that as one increases, the other also increases. So as temperature increases, volume increases. As temperature decreases, volume decreases. Now with Charles' Law and with all these laws we go over, you're going to want to make sure you take down this graph, what the graph should look like. So you have volume on the y-axis, you have temperature on the x-axis, and you can see that it's increasing. As the volume is going up, the temperature is also going up, and vice versa. So that's an important graph right there. And this is an example of a direct relationship, meaning they will both increase and decrease together. This is just another example of the graph. You can see that the temperature is getting higher towards 200 Kelvin, and the volume is increasing towards 3.5. So an important note right there. An example of Charles' Law in real life, everyday life. If you're playing like a winter football game, like it's cold outside, below freezing, and you inflate the football inside, and then you take it outside, it will actually shrink slightly, and you'll have to re-inflate it once you get outside. The reason for that is when the temperature decreases, if it's being inflated inside and it's 70 degrees inside, when you go outside and it's 32 degrees, the ball is going to shrink because the temperature is going down. So the volume and the temperature are both going to decrease. So that's a real-life example there of how that can happen. You have to re-inflate the ball before you start to play. Okay, some example problems here for Charles' Law. I just have two of them right here that we are going to do. So we have number 1, the Fighting Farmers are prepping for a game versus the Flower Mound Jaguars. The Louisville footballs are inflated inside the field house where the temperature is 30 degrees Celsius to a volume of 1.2 liters. Outside, the temperature is 0 degrees Celsius. What would be the new volume of the footballs once they are taken outside? So just like our previous laws, the first thing we want to do is identify the numbers we are dealing with. And what is V1, and what is T1, and what is V2, and what is T1 and T2. So the first thing we see is 30 degrees Celsius. So that is going to be T1, because that's the first temperature we see, T1. Then we see 1.2 liters. So that is going to be V1. So we already have our first part of the equation. We have V1 and we have T1. Now let's identify what else we see. We see another temperature, 0 degrees Celsius. So that is going to be T2. And then if that is T2, then that means that we are solving for V2. We don't know what V2 is. So then we just plug everything in and solve. But before we can solve, we have to make sure that we convert Celsius to Kelvin. So how you convert Celsius to Kelvin is you just add 273. So you got 30 plus 273, and that is going to equal 303 Kelvin. And that is going to be our T1. And then you have 0 plus 273, plus 273. And that is going to be 273, and that is going to be our T2 in Kelvin. That's the first thing you should do, is make sure that you convert to Kelvin. That is step 1, is converting to Kelvin. Now we can go ahead and set up our problem. So we have V1 over T1. Our V1 is 1.2 liters. It's already in liters, so we're good there. We don't know our V2, so that's going to be X. Our T1, as we just went over, is 303 Kelvin. Whoops, Kelvin. And our T2 is 273 Kelvin. And so what this is going to allow us to do is see if we were to have footballs in this situation, what our new volume would be once we took these outside and the temperature decreased by 30 degrees Celsius. So we'll be able to see the decrease in volume after we solve this problem. So you solve it the same way that we always solve when we have these proportions, and that is you do a cross multiply and solve, so you end up with 303x equals, and then you do 1.2 multiplied by 273, 1.2 multiplied by 273, and that equals 327.6 as of now. Then we just divide by 303. You always divide by whatever is by the x. So you have to divide by 303 on both sides. Divide by 303. 303. So 327.6 divided by 303. You end up with 1.09. So we're just going to go with 1.1. You end up with 1.1 liters. So our new volume of the football after we have moved outside and it has decreased by 30 degrees Celsius is 1.1 liters. So you'll see that's just 0.1 liter smaller than the original volume. So that shows you it has to be a pretty significant decrease in temperature to have any significant decrease in volume in terms of like a football that is that small. So that's our first example. Let's quickly run through a second example here. Our second example. A container of 12.1 liter gas, so we already can see there, that's going to be the first thing we see, that's going to be our V1, is kept at a temperature of 285 Kelvin. So 285 Kelvin, that's the first temperature we see, so that is going to be our T1. The temperature is increased to an unknown amount and the volume increases to 45.2 liters. So 45.2 liters. Is that a volume or a temperature? It's a volume, so it's going to be our V2, meaning we are solving for T2. So as we solve this, it's here, here. Okay, as we solve this, our V1 is 12.1 liters. Our V2 is 45.2 liters. Our T1 is 285 Kelvin. No conversions necessary because it's already in Kelvin. And we are solving for x, which is going to be our T2 because we're not given a T2. So let's set up our proportion here. Set it up, equals. And then we will cross multiply and solve. So you end up, of course, with 12.1x. And we are going to set that equal to 45.2 multiplied by 285. So 285 multiplied by 45.2. And that equals 12,882. Then, what do we divide by? We divide by whatever's next to the x. So divided by 12.1, divided by 12.1, and we will get our answers. 12.1, 12.1. Divided by 12.1, you end up with 1,064.6. We're just going to round to 1,065. So you end up with 1,065, and what's our unit of measurement here? What's our new temperature? It's got to be Kelvin. Our unit of measurement has to be in Kelvin. So 1,065 Kelvin, so that's an exceptionally high temperature for this container of gas. And how I knew that we were measuring in temperature, I just looked right here and it was what is our new temperature? And you just have to remember that temperature is measured in Kelvin. So those are your first two examples of the wonderful Charles law. What a great equation. Farewell.